All right, so we finished up on Tuesday doing some shell method stuff. Our three basic methods are disk, washer, and shell. The first method we had we called general slicing. So we really have four methods of finding these volumes. The general slicing method, as a reminder, we had a base, so a region in the XY plane, and then we said, hey, let's stack a bunch of squares or a bunch of semicircles or a bunch of triangles. So we sort of created the solid object by defining what the geometric cross-section would look like. And then we got to the disks and the washers where we created those by rotation. And now we've got this shell method, which is kind of like the disk and the washer method in that you have cross-sections, except that the cross-sections aren't cross-sections in the traditional sense. They're not horizontal cross-sections. They're cylindrical cross-sections. So we're thinking of all these nested cylinders. But the concept is the same. We're filling up the volume with a geometric shape that's replicated lots of times. So here we have one where we're going to rotate around a non-axis axis. So a vertical line that's not the x-axis or the y-axis. A vertical line that's not the y-axis. So a non-coordinate axis. The shape, the region, capital R, is going to be defined by these three boundary curves. So we've got y equals x squared, x equals 1, and y equals 0. So that creates our trapped region. So our region has those three boundary curves. If a lot of times they don't do the graph for you, and they just give you the boundary curves. So make sure that you can graph basic boundary curves. Quadratics, e to the x, natural log of x. So the sort of basic curves. There's our boundary curve right there. There's our region. And we want to rotate around x equals -2, which is way over here. So we're going to take our region, rotate it around x equals -2. And we're going to use shells. So we're told to use shells. You could look at this and say, hey, this is horizontally simple also. You could draw a horizontal integration element and rotate that horizontal integration element, and what shape would you get if you did a horizontal rotated around that axis?
That'd be a washer.
That would be a washer. So if our axis is over here and we chose a horizontal integration element, that would rotate around creating a washer. So we could do it that way. And if we did do it that way, we would need to write both of these boundary curves as x values. We would have to solve for x because everything would be horizontal. All right, they tell us to use shells though. So if we're going to use shells, we are going to choose a vertical integration element so that we're parallel to the axis of rotation. If the element is parallel to the axis, that's going to create the cylinder. Perpendicular creates a washer. Parallel creates a cylinder. So there's our integration element. We say that this is at a random x. And then once we know our shape, disk, washer, shell, we write down the generic formula for the area of that object. So for a cylinder, we have 2 pi r times h. So the area of a cylinder. Area of a cylinder, 2 pi r is the circumference. H is the height. That's going to give us the lateral area of a cylinder. Now we have chosen a vertical element. The thickness of that vertical element is dx. That tells us we're going to integrate with respect to x. Everyone okay on that part? So if it's vertical, we integrate with respect to x. If it's horizontal, we integrate with respect to y. So we're going to integrate with respect to x. That tells us that the r and the h have to be replaced with expressions in x. So we have to turn them all into x's. We can only have x's in there. So let's first take a look at the radius. So the radius of this big cylinder, there's our representative cylinder down there. The radius is that distance from the axis of rotation all the way over to our representative element. That's the radius. And we have seen that the radius is sometimes just the x or just the y. But is that the case here when we have an axis that's not the y-axis here? How far is that element x from this axis of rotation?
X minus 2.
Close.
X plus 2.
X plus 2. It's x minus minus 2.
Okay.
The right x, if you will, is just x. The left x is negative 2. To get a horizontal distance, we take the right x value and subtract off the left x value. So it would be x minus minus 2. Or you can think kind of absolute value. You could say, oh, the distance from the x-axis over to the line x equals negative 2. That distance is x. And the distance from the y-axis over to x is x. So that distance right there is x. This distance right here is 2. So the radius is going to be x plus 2. So a couple ways you could think about that. Either one works. And now we want the height. And what would the height of our representative element be?
X squared.
X squared. Because this function right here is y equals x squared. That sloped function is y equals x squared. So we are going to replace that height with x's. So the one thing that's a little bit complicated about shells is that we have both a horizontal piece and a vertical piece. Whereas with discs and washers, everything's going in the same direction. You're either dealing horizontal or dealing vertical. You're not dealing with both at the same time. So there is our cylindrical area at a random x. So all these x's between 0 and 1, that's going to be our integration interval. That's where the region is. The interval always has to come from one side of the region. So our limits of integration will be 0 to 1. We will have cylinders for all of those x's between 0 and 1. And the idea is that if we take the area of our cylinder and multiply it by dx, we then have a slice. We have a cylinder that has a little bit of thickness, a little bit of volume. And then if we add up all those little cylindrical volumes, we'll get the total volume. That is our strategy. So the volume will be the integral from 0 to 1, and we will distribute this x squared. That is our volume formula. So all we do is integrate area with respect to x, and that's going to give us the volume of that stadium-looking thing. The 2 pi can come to the front, and we can integrate with the power rule. We add 1 and divide by the new exponent. So we'll have x to the 4th divided by 4 plus 2/3 x cubed. And that will go from 0 to 1. So is there any piece of that that you're not sure about yet? Mm-hmm.
Why are we integrating from 1 to 0 instead of 2 to 0?
So we are imagining where all of, so if we choose a vertical element, we imagine the interval where all those vertical elements are standing. So these vertical elements are all standing on this interval from 0 to 1. So we are looking down here at that left endpoint and that right endpoint there. So if we have a dx, we have to look onto the x-axis and figure out where those elements live. So there's no elements to the right of 1. There's no elements to the left of 0. All those little red rectangles are stuffed inside 0 to 1. So we're always going to look down at the, if we're integrating with respect to x, the x-axis. And then we imagine all those little rectangles stacked next to each other, figure out what that range is. So they go from 0 over to 1. Does that make sense? Any other part of the setup here that you want to ask about? Once we do our integration, 0 is not going to contribute any volume, so we just have this. We'll get a common denominator of 12, so we'll have 2 pi, and then we'll multiply by a fraction with a 12 on the bottom, and we'll have 3 plus 8 in the numerator. So we'll end up with 11 pi divided by 6. So a little bit harder when the axis is not a coordinate axis. There's a little bit more thinking involved, especially in figuring out the radius here. That was the big piece that was different. We had to sort of think about not just the distance to a coordinate axis, but we had to go a little further. Let's try another one. So here we have this region. So this is the same exact region, x squared, x equals 1, y equals 0. Same region, but we are going to rotate around this line that's up high, up at y equals 2. So we're rotating around that line. We want to use shells. The axis of rotation is horizontal. To create a cylinder, we will use a horizontal element so that our integration element is parallel to the axis of rotation. That's how we create a cylinder, parallel. So right away we know that the geometric shape that we're using is a cylinder. So we can write down the generic formula for a cylinder. So 2 pi RH, area of the cylinder. And then we have to think about whether we want to turn the R and the H into Y's or into X's. And we look and we're like, okay, we have a horizontal integration element. This is at a random y. The thickness of a sleeping rectangle is dy. So we know we're integrating with respect to y. That means we have to turn the R and the H into y's. So we come over here. Let's identify the R and the H. So the radius is going to be from our element down to the axis, or up to the axis of rotation. So right there, this is our radius. So it's the distance from our representative rectangle, our representative integration element, up to the axis of rotation. That is our radius. So that's the radius of the representative cylinder that we're thinking of. We can't draw all the cylinders. We just grab a representative one. So we create a representative element, which creates a representative cylinder. And then if we multiply by dy, then we add some thickness to that cylinder, giving it volume. And then we add them all up. Okay, so that radius is a vertical distance. Anytime we want to find a vertical distance, upper y coordinate minus lower y coordinate. Right? If you're on the y-axis and you want to know how far apart 2 points are, take the big one, subtract off the small one. Upper minus lower. So we look here and we notice that the upper y value right there is 2. Right? Top of that, that's 2. And the y value right here, oh, we've called it y. Right? That's got to change. It's moving. It's any number between 0 and 1. So if we pick a random one, we just call it y. So that distance is 2 minus y. The y value up there is 2. The y value down here is just y. So we're going to call that 2 minus y. And then the height of this cylinder is right there. Excuse me. Well, the height of the cylinder, yes. Height of the cylinder is given by that element, that representative element, and the height is sideways. So the height of the cylinder is a horizontal distance. Anytime we find a horizontal distance, we think about x's, the right x minus the left x. That gives us horizontal distance. So we come over here, let's identify. All right, so this x value over here, that's x equals 1. This x value on the left, the function is presented as a y value, right? It's presented this way. That's how it was given to us. We need to convert it so it's presenting as an x value. It's measuring horizontal instead of vertical. So we take the square root of both sides. Now, whenever we initiate a square root, we get a plus or a minus. But we are in quadrant 1, so we should choose the plus. We're in quadrant 1, so x's are positive here. So we're going to take the positive square root of y. So that is the right x value, the left x value. So we've taken the curve, we've taken the function, we've rewritten it so that it's measuring horizontal, which is what we want. So this x value right here is measuring this distance from the y-axis over to that curve. That's what it's measuring. So if we do 1 minus it, so 1 minus root y, that will be the height of that red segment, or the length of it. And that will be the area of the cylinder at any y value. Now our limits of integration are coming from the y-axis, right? So this is where we're thinking about all of these cylinders being nestled together. There's a cylinder for all of these y values between 0 and 1. So the 0, 1 here is vertical, unlike the last one, it was horizontal. Right? These cylinders are created by y values between 0 and 1. Okay, so when we go to find our volume, we are integrating 0 to 1 again, just like the last one, but these are y values, 0 to 1, not x values. Let's go ahead and multiply this out, FOIL it. So we're going to have positive y to the 3/2 minus y minus 2 square root of y, which we can write with a fractional exponent, plus 2, and then dy. Setup complete. Any questions on any of those components of that integral?
Actually, this is for the area. Why did we do 2 minus y instead of 1 plus y?
So with this radius, we want that blue distance. It's vertical, so we take the y-coordinate at the top and subtract off the y-coordinate at the bottom. So this y value right here, that's measuring this height right there, right? That height right there is y. But we're trying to find this distance right here. So we take the total distance, which is 2, and then subtract off the y to get this distance. You see it? So anytime we have a vertical distance, it's top y minus bottom y. And the top y up here is 2. The bottom y is just y. So it'll be, that blue will be 2 minus y. The full distance is 2. And then we're going to subtract off that little piece to get this complementary piece. That makes sense? And now we can do our regular integration using power rule. So we will add 1 to the exponent, creating y to the 5/2. And then we will divide by 5/2. And that will be our antiderivative. The 0 contributes no volume. So we just have to substitute in the 1. So we will have 2 pi multiplied by all of this. Common denominator of 30. We have 3 prime numbers in the bottom, so we have to just multiply them all together. Common denominator of 30. This one gets multiplied by 6. This one gets multiplied by 15. That one gets multiplied by 10. That one gets multiplied by 30. Whatever that turns into. So we're going to subtract off 55 there, so that's 5. That's 17 pi divided by 15. All right, any lingering questions? The integration okay? Add 1 to the exponent, divide by the new exponent. If you divide by a fraction, you multiply by its reciprocal. Foiling, hopefully you're foiling, like I've said a bunch of times already, all the algebra is coming back. Yeah?
How do you get 4/3 y 3/2?
So when we add 1 to the exponent here, we're adding 2/2, getting 3/2.
Right.
If you divide by 3/2, you multiply by 2/3.
Oh, and the 2 at the constant.
2/3 multiplied by 2 will give us the 4/3.
Gotcha.
Yep. All right, let's go to the napkin ring. So back in the old days, they used to use these things called napkin rings, where they take a cloth napkin and stick it through it. Maybe some of you have never seen a napkin ring. I don't know. So we call that shape the napkin ring. It's basically just a sphere with a hole drilled out from the middle. So that's the napkin ring. This is a top view looking down through the hole in the napkin ring. This is kind of a vertical cross section. And we can imagine that this napkin ring is created by taking this region here and rotating it around the y-axis. So that region can be thought of as our generating region. And then we rotate that around the y-axis, and it's going to create this so-called napkin ring. So there is our napkin ring's generating region right here. So we want to find the volume of the solid created by rotating that around. We're told that the sphere has a radius of 6, and we're going to drill out the core with a radius of 3. So this outer, bless you, this outer circle has a radius of 6, so that's what that equation looks like. X squared plus y squared equals 36. And if you were to look at the top half of the circle, the top half, you would solve this for y and choose the positive square root. You would choose the negative square root for the lower half of the circle. So there is the equation of the upper half of the circle, right there. All right. Now, the reason I need the upper half of the circle is that if we're going to use cylindrical shells, we're rotating around the y-axis here. That's a vertical axis that we're rotating around. That means we need to choose a vertical element. The boundaries of this vertical element are here at y equals 0, and the other boundary is here, and that's going to be y equals that positive square root of 36 minus x squared. Okay, so we are once again using cylindrical shells, And we know that the area of a cylinder is 2 pi radius height. That's the area of a cylinder. We see our vertical integration element. That means its thickness is dx. That means we integrate with respect to x. That means we turn the r and the h into x's. Now that vertical integration element, when it rotates around the y-axis, it's only creating half of our napkin ring. Right? It's creating the top half. So what will we do to get the entire napkin ring? Double it. And we can think of this in two ways. You could think of this doubling as extending this element all the way down to here so that you're rotating complete elements all the way around. Or you could think of the doubling as literally finding the upper volume and then multiplying by 2 to include the lower volume. So you can think of it in either way. But we're going to need to double. Because that function there only measures from the x-axis up to the curve. It's not measuring the whole distance right there. It's not measuring the entire height of that. You know, it's not, if we were to draw a full element all the way down, the height of the cylinder would go from the bottom to the top of this circular piece. This function only measures that top part. So we have to double it to measure the whole thing. All right, so 2 pi, the radius. So once again, the radius is the distance from the axis of rotation over to the element. And this is a random vertical element at x. X is going to be in that little x interval there from 3 to 6. And the distance from the axis of rotation over to that element is what? Is what? Yeah, just x. Right? This, if we draw this vertical element and we say, hey, that vertical element is at an x value of x. Well, x measures the distance over to the axis of rotation, which is the radius. So the r value is going to be just x. Whenever we do shells around a coordinate axis, you typically are going to end up with your radius being just x or just y. Now the height of the element, so we're going to focus just on this piece up here in quadrant 1. The height is given by the function. So the height of the element is the function. So our function is 36 minus x squared square rooted. So there's the area of the cylinder at x. And again, this is just going to be the upper half of the napkin ring right now. When we go to find volume, here's where we're going to throw in our symmetry. So that is a symmetry 2. That 2 is by symmetry. You can think of it as doubling the upper volume, or you can think of it as doubling the element to create a full-length element. Doesn't matter how you think about it. And then we can pull out the 2 pi. And then in here, I'm going to write this with a root symbol just to do it. What about our limits of integration? What do you think they are?
3 to 6.
3 to 6. We're integrating with respect to x, so we should be thinking about the x-axis. And we want to look and say, well, hey, where are these vertical elements located? So those vertical elements are located right in there. So those go between 3 and 6. Those will be our limits of integration, 3 to 6. So that will be our volume. What technique of integration would we use here? Substitution. And this works great because when we let u be what's inside the square root, its derivative is present on the outside. If we divide this by -2 right here, the derivative gives us this formula where we're looking for an x dx. There is x dx right there. So that will be the technique of integration that's going to work. And I'll just go one more step, and if I've got the answer up here. If you want to continue and get to that answer, very cool. So what I'm going to have in here is the square root of u, and then x dx becomes du divided by -2. So the du divided by -2, we put the du in the integral, the -2 outside. How about limits of integration? If we're going to convert over to u limits, what would this 3 become in terms of u? So these limits are x equals 3, x equals 6. How do we get to u?
Plug in 3.
Plug in 3 for that x right there. We get 36 minus 9. That's going to be 27 as our lower limit of integration. Upper limit, we plug in 6 and we get not a lot. How much? 0. Right? 36 minus 36. So there is our, we might as well finish it off. We're so close now. Do you all remember this? That we could flip the limits of integration and multiply by -1? We wanted to? We would flip the limits of integration, multiply by -1, which would just wipe out that minus out in front. Could do that. Don't have to. They'll cancel at some point. So then we're going to get the u to the 3/2 divided by 3/2 from 0 to 27. So we will have 4 pi divided by 3. Excuse me. 0 is going to contribute no volume. The 27, we are going to end up with 27 to the 3/2 power. And quite frequently, what we'll do when we have a 3/2 power, there's multiple ways to simplify it. You can do the denominator first, take the square root of 27. Another way is to do this. We could write this as 27 root 27. Anytime you have a 3/2 power, you can do that. Like if we have, say, 5 to the 3/2, this means that you could take the square root of 5 and then multiply itself 3 times, and that is going to give you 5 times the square root of 5. So if you have a 3/2 power, that's typically how we end up writing it. Right? This is the square root of 5 3 times. Square root of 5 times square root of 5 is 5. So we could do this. Now, square root of 27 is not simplified yet. And we also have a cancellation here. 3 goes into there 9 times. So we're going to end up with 36 pi. 9 times 3 here, which turns into a 3 root 3. So that's going to be 108 root 3 times pi. All right, any part of that that you have a question on? If you have a question, someone else has a question. We know that rule. Yeah?
Did you help me in identifying that substitution would be the best option here?
Yes. So when we look at an integrand, you don't have that many techniques yet. If you have an immediate antiderivative, of course, then you go that way. Like if you're integrating sine, you know, oh, negative cosine is the immediate antiderivative. But here, we don't have an immediate antiderivative. You don't know a function that's going to have a derivative equal to that. This is a product, right? So then the next natural choice is to look for substitution. Frequently, substitution is used when you have a product or an exponential with a, some sort of complicated looking exponent, or when there's a square root, it is very common to use substitution. And so the piece that I say to myself is, would substitution work? And you look at what you would substitute. Usually it's what's in the exponent, what's in the angle, what's in the square root. It's sort of the inside of something. And the derivative of that is negative 2x. The important part about the derivative here is that it's linear. Right? Negative 2x is a linear function. And we see this linear function out here. So that's kind of how we know substitution is going to work, because the derivative of the quadratic inside the square root is linear, and we see a linear function outside. And that linear function multiplied by dx is right there. So we're able to create from the substitution's derivative whatever's outside. We can clean up what's outside the square root with that derivative.
Cool. And then a follow-up question. When you flip the integration, that minus 2 becomes a positive 2?
Yes.
Okay. Cool.
So anytime, it feels more natural, and you can imagine it in your mind here. You're going to end up, when you do your limit substitutions, you're going to end up with plugging in 0 and then subtracting off the 27 substitution. So it's that idea. We're just flipping that.
Okay.
So if we flip it, this is more natural to integrate, from smaller to bigger. You don't have to, of course, but if you do, then you just multiply the front by minus 1.
Okay, cool.
Yeah.
How'd you get from 27 3/2 to the final answer?
So 27 to the 3/2 power is the same as that. And it's the same as that because of this. If you have a 3/2 power, the denominator is a root, the numerator is a power. And so if we trigger the denominator first, that's square root of 5. But then the 3 says multiply it by itself 3 times. And if you multiply it by itself 3 times, if you take 2 of them and multiply them together, you get rid of the square root. So it's always going to be that way if you have a 3/2 power. So if we have something like 2 to the 3/2, that is going to be 2 times the square root of 2.
Okay.
So whatever that base is will be without a power and then a square root of it. So it'll always be that way. Then this one has just the extra complication that this still isn't simplified. So whenever we have a 3/2 power, this is sort of the way that we usually are going to write it as a simplified form. And you can think about here, like at this stage, if you wanted to go backwards, this is 21 to the 1 times 21 to the half. If you were to multiply exponential expressions with the same base, you add the exponent, so you'd have 21 to the 1 plus a half, which is 3/2.
Okay.
You see it?
Yeah.
All right, let's go to our, that's the end of this. Is that the end of this section? Yeah, end of the section. Let's go, 6.5. Okay, so 6.5 and 6.6 are going to involve some integrals that are a little unsavory. Arc length and surface area tend to be topics that create integrals that you can't always integrate by hand. There's going to be square roots that just sort of stink. So let's first talk about a concept that you first learned in Calc 1, and that is this idea of a differential triangle. So we are on a curve, and we're going to use the letter S to measure along the curve. So you can kind of imagine a string with a little number line on it measuring along the curve. All right? So back in Calc 1, you learned that the increment is given by the triangle, Greek letter D, Greek letter delta, D for difference. So delta S is the exact change in the position along that arc. All right, but we don't know that, right? We don't have that string number line where we could say, oh, S is 0.5 here and S is 3.2 here. Then we could just take the difference, right? If it was along the x-axis and we were told that we have a 3.2 and a 0.5, we could just subtract them. but we don't have this number line that's curved, so delta S is unknown. But delta S can be approximated by that ds. So our differential triangle has a dx in the horizontal direction, a dy in the vertical direction, and ds is the hypotenuse of it. So ds is going to approximate delta S. Delta S is the exact arc change. ds approximates it. Now, one thing that might not have been crystal clear in Calc 1 is that this approximation piece is always with your dependent variable. So in Calc 1, you said that dy was approximately delta y, and you said that dx was exactly equal to delta x. So your independent differential and your independent increment are always the same. And with this scenario, our variable is the s piece, and dx and dy are considered independent, not dependent. And so in this context, we would say that dx equals delta x and dy equals delta y. So it's always the dependent variable where you have this approximation thing that we're doing. And in Calc 1, you only had one independent variable. X was your independent variable, so you had dx equals delta x, and then dy and delta y were approximately equal to each other. Okay. All right. Now, again, if we were trying, so let's back up for 1 second. If we integrated dx from 2 to 3, no, let's go 2 to 5. 2 to 5, what is that answer? Three. If you integrate a differential, you get the length of the interval. Right? If we were to do the math here, you would say, oh, well, the integral of dx that's a 1 dx. So you integrate that, you get x from 2 to 5. That's going to be 5 minus 2. You get 3. So anytime you integrate a differential, you just get upper limit of integration minus lower limit of integration. So that's like you're on the x-axis, and there's 5, and there's 2, and you're just trying to find that distance. If we're on the curve, we are integrating ds. ds is measuring along the curve. So if we happen to have s limits, we could just do that. But once again, we don't. We don't have a curved number line. So if we're trying to integrate ds, we need to do some sort of mathematical substitution to get to x's and y's, because we know how to integrate horizontally and vertically. If we integrated dy from 1 to 3, what would that be? 2. Right? The integral of a differential is always the length of the interval. So this means that we have y limits. This means that we have x limits. There's no way for us to create s limits, so we have to do some sort of substitution. And here's what we do. You stare at that and you're like, oh, it's a right triangle. Well, if it's a right triangle, we use that. And wow, my thing vanished. Where did it go? I just did this before class. There's supposed to be a formula right there, and I don't know why it's missing. It was in there before class. Let me go grab the formula. So, shucks, I don't have that notebook opened. So, what we are going to do is we're going to use that Pythagorean theorem, and that Pythagorean theorem, we need to somehow get rid of the square root on the right-hand side, and we need to get to either a dx or a dy on the outside. And here's how we're going to do it. Hopefully it loaded properly in my set of blank notes. Yeah, there's the formula. So Control, copy. Let's go back to our notebook. That was supposed to be right here. All right, it's there now. All right, so a little bit of algebra. If we want to replace the ds with something, we're going to take the square root of, we're going to isolate ds by taking the square root of both sides, and we're going to choose the positive square root because we're measuring distance. Now, replacing this ds with that square root doesn't help us. We need a dx or a dy on the right-hand side so that we can integrate. Not a dx squared, not a square root of dx. We need a dx or a dy so we can perform integration. So all we're going to do is some little algebra here. What is our sorcery? Our sorcery is that you've seen many times as you multiply by 1. It's like the simplest sounding thing. It's like the silent killer. All we do is multiply by 1 and all of a sudden things unfold beautifully. So we're going to multiply by 1 in the form of dx squared over dx squared. That allows us to factor dx squared. There's now a dx squared common to both terms. That can jump through the square root as just a dx. Factoring out dx squared becomes a dx when you factor it out of a square root. Dx squared out of dx squared creates the 1. And if we pull this dx squared out to create that, then we have dy squared over dx squared, which is dy dx squared. And we'll typically write this as the square root of 1 plus y prime squared dx. That's usually how we'll write it. Now we have a dx on the outside. Once we have a dx on the outside, we can say, okay, well, what are our x limits? So we're going to come down here and find our x limits right there, the a and the b. So that's how we're going to convert an arc length interval, an arc length integral. An arc length integral has a ds as its natural differential, but we can't do anything with it. So we're going to convert it over to something we can do something with. So we're going to convert ds into the root of 1 plus y prime squared multiplied by dx. All right, so that is our formula for the arc length when we're dealing with functions of x. So let's try it. So here's our function. When we're doing arc length or surface area, we must find the derivative. That's kind of the first step. So we have our function, y equals 4 minus 3x. The derivative of this function is negative 3. So the arc length is going to be the integral. They tell us we want to go from negative 3 to 2. And all we have to do is replace the derivative inside here. That'll be the arc length. So the square root of 1 plus the derivative squared. That is going to be the arc length. So this becomes negative 3 to 2. This is a constant, root 10. And you should, let's just get this root 10 pulled out. What is the integral of dx from negative 3 to 2? 5. It's the length of the interval, always. So the answer here is 5 times the square root of 10. Make sense? Let's try it a second way. Let's say we wanted to integrate with respect to y instead of with respect to x. So if we wanted to do it the other way, we would do this. We would say, okay, well then s will equal the integral of 1 plus x prime squared dy. And we're going to go from c to d. C to d will be on the y-axis. C would be there and d would be there. So we went on the x-axis with respect to x, so we had limits of negative 3 and 2, so we were right there on that interval. Now we're going to do it the other direction, so this is our interval of integration. So let's see if we can do that. Okay, well I see, which isn't always 100%, but we can do the math too. If we plug in the negative 3 right here, we get 13, and I can see that it's 13 on the graph, and it lines up properly. So, whoops. Negative 3 is 13, so that's down here. So negative 3, and then 2, when we plug in a 2 up there, we get what? -2. So that would be our conversions. Now, there's one thing I want to modify. So all I was trying to do is figure out these points right here. So I figured out that this y coordinate here is 13. Figured out that this y value here is -2. And I kind of put them in the same place on the integral like we do substitution, but we don't actually do the same type of thing here. All we wanted to do was figure out what those numbers were. When we look over at this scenario, we want to be integrating from down here to up here. We want to be going from -2 to 13. It's not going to matter that, we're not doing a substitution where this x gets turned into this u, so it has to be in the exact same place. When we look at this overall picture, there's our integration interval is right here. So -2 to +13. Now we have to find x prime. Well, the function is presented as a y value, right? 4 minus 3x. Right, 4 minus 3x. So if we want to take x prime, we have to reconfigure this function so that it's an x value. So we have to isolate x. I'll write it like this. What is the derivative here? What is x prime of y?
Y.
-1/3?
Oh, yeah.
The coefficient of y. The coefficient of y. So then in here, we get 1 plus the derivative squared. The derivative squared is 1/9, and our integral is with respect to y.
So you had in the past flipped our integrand or integral by multiplying by a -1.
Yes.
And so I may be a little confused, but
Yes.
it seemed like you were saying it didn't really matter which number went where.
So let me try to clarify that again. I wrote because we had just been doing substitution, if you have an integral and you've got your limits of integration and you convert from, say, x to u, those limits have to be in the same position.
Yeah, absolutely.
Absolutely. Here, I kind of had that in my mind, and I did that same process, but we're not converting from these limits to these limits. This integral is completely different than this. So what I should have said was we look at the -3 and the 2. We want to find the corresponding y coordinates. And then when we integrate, we're going to integrate like we normally would. This is the lower, this is the upper.
So it would be incorrect to do 13 to -2.
It will end up with a negative number.
Okay.
And if we're finding arc length, we know arc length is positive, so if you did end up with a negative number, you could either just take its absolute value, or you think, oh yeah, I switched the limits of integration.
Okay.
So it's a totally different process than doing the substitution conversion limits. And I shouldn't have written them there to start with, because my goal was just to figure out what are the y's. So what are the y's? Whatever the y limits of integration are, we go from the bottom to the top. So it's totally different than u substitution, which I should have been more careful with. Okay, so let's go ahead and finish this. In here, we're going to get common denominator of 9, so we're going to get 10/9. So we're going to get the square root of 10 over 3 dy. And this will be the square root of 10 over 3 multiplied by? Did I do that right? That's 9 plus 1 is 10. Square root of 9 is 3. What's the length of this? Isn't that 11? Oh, no. 15. Thank you. Oh my gosh. I was panicking for a minute because the numbers were not matching. I was doing 13 minus 2 instead of 13 minus minus 2. So 5 root 10, which is the same as we got above. Yeah.
And how did you get that root 10 over 3?
This is 9 divided by 9.
Oh, actually, I
You see
already
it?
see it, yeah.
So we're going to multiply that by 9 over 9. So we have 10 over 9. Okay, let's try another one. We'll do one more and then we can take our break. Okay. Oh, yeah. You'll need a break after this one. Okay. So back to algebra 2. Back to high school algebra. These are your two perfect square trinomials, all right? Those are both perfect square trinomials. That's how they factor into x minus b squared and x plus b squared. What is the only difference between these two trinomials over here?
The signs of the two.
The sign of the middle term. That's the only difference. The sign of the middle term is different. That's it. So keep that on the back burner, that your two perfect square trinomials differ in one way. The minus sign. Okay, so keep that in mind. Here we go. So anytime we're finding arc length, we are going to need the derivative. So let's go ahead and find the derivative of this function. Natural log's derivative is 1 over x. So we end up with 3 divided by x. And then the derivative of that square, we pop the 2 down, we subtract 1, the 2 cancels with the 24, giving a 12. So we're going to have x over 12. And our interval is down here on the x-axis. So that interval, whoops, and it goes all the way over to 6. So that interval is given 1 to 6. If we were going to integrate with respect to y instead of x, we would go from 0 up to whatever this is. So with an arc length integral, you're always integrating left to right or bottom to top. If we wanted to convert it, we could. Okay. Now, the integral has this square root of 1 plus the derivative squared. So we have to square that derivative. So when we're squaring that derivative, when we're squaring this binomial, right, it's got 2 terms, we're sort of in this position, right? We have an x minus b, an a minus b, and we're going to square it. So we're going to think of this as a, this as b. Everyone with me? So a and b, the minus is not part of the b. It's a minus b.
So the 3 over x, you got that from the derivative of the natural log.
Yep, so it's 3 multiplied by the derivative of natural log of x, and the derivative of natural log of x is 1 over x.
Okay.
And the integral of 1 over x is natural log of x. Natural log of absolute value of x. But yep.
And for this class, as long as there's not a parentheses, we have to assume that the negative minus
Yes.
is going to be out.
Right, so if we wanted this piece to be inside the log, we would have to have that. So if there's no parentheses at all, as soon as you come to a plus or a minus, you're outside. Yeah, it would be convenient if we always wrote, that, but we don't. Everyone wants to write the minimum possible so that we're not getting too tedious. But yeah, good question. So that minus x squared is outside. So let's square this. So y prime squared, and I'm not going to simplify. So there's a squared minus 2 times a times b plus b squared. So don't simplify anything. So we have that. So we're just using high school algebra foiling. Right? A squared minus 2ab plus b squared. Now notice that, let's just leave this unsimplified on the front and the back. Let's just leave this alone. And let's just focus on the middle term. So only focus on this term here. What does that all simplify to? Well, the x's are going to cancel. We have 2 times 3, which is 6, divided by 12, so we get negative 1/2. So that's what the middle term simplifies to. We have 2 times 3 divided by 12, that's a half. Minus sign. Now our formula here says, okay, now add 1. So here we go. Here's the perfect square trinomial. Sneaky. So now we're going to add 1 to y prime squared. What changes when we add the 1? What does the middle term become?
Plus 2ab.
Positive 1/2, right? If we add 1 to this, it becomes a positive 1/2 in the middle, and the front and the back just stay the same. Correct? Right? We just add 1. We can combine the 1 and the negative 1/2. We get a positive 1/2.
So you're adding 1 to both sides?
Both sides.
Oh, okay.
Yep. So we're trying to, inside the square root, we have to create a 1 plus y prime squared. So we've got y prime squared right here. Now we want to get to 1 plus y prime squared, so I'm going to add 1 to both sides. What's the only difference between these two trinomials?
The sign of
The sign of the middle term. Right there, the sign of the middle term. So this then tells us that, oh, now we have a plus b quantity squared. That's how that factors. If you were to simplify this and write it as 9 over x squared and x squared over 144, you would never, ever, and then add 1 to it, you would never factor it into this. It would never be obvious to you that that was a trinomial that you could factor. But if you leave it like this, you do your a minus b squared, you add the 1, you're like, oh gosh, the only thing that changed is the middle term sign. Then that tells you instantly that it factors to that. And if you FOIL this out, you will get back to this. 3 over x squared, x over 12 squared, this times 2 will be that. You will get that. So now this is super sneaky, but now we're to the point where we have this. So our integral, the x interval is 1 to 6, and the integral of the square root of, we just found that 1 plus y prime squared is this. So we have 3 over x plus x over 12 quantity squared times dx. What happens with the square root of the square?
They cancel.
They annihilate each other, they cancel. So we're left with the integral of the stuff that's, can I write that properly? Let's see. A little too high. So we integrate this, right? So the square root and the square cancel. So we end up with this. This will be 3 natural log of absolute x plus x squared divided by 24, interval 1 to 6. Question, good point, good observation. So we started with y prime being 3 over x minus x over 12. We end up with the same thing except with a plus. That is one of your mental cues that you're on track, that you did this right, is that should match that except for the middle sign. Okay, so now let's just finish this off. This is going to be 3 ln of 6 plus 36 over 24. And then we subtract off antiderivative evaluated at 1. Natural log of 1 is 0. So the only thing we subtract off is a 1/24. So this will give us 3 ln of 6 plus 35 over 24. No common factor in there, so we'll just leave it like that. All right, let's go ahead and take our 10-minute break and stare at that thing for a minute or 5 and let me know if you have questions on it. Let me just pause the recording.
Easy.
We're waiting for
It's
this
like-
race. Yeah.
Y'all are gonna win this race, guys.
All All right, so here's we'll do one more of these trinomial ones, and then you can look at them over the weekend, and we'll on Tuesday, if you get hung up on them, we can take a look again. So there's a couple of checkpoints that I want you to observe as we're going through these perfect square trinomial ones. So the function has to be very cooked up in order for this technique to work. If you pick a random function, this is not going to be the technique. Look at that function. So this function has to have some very specific properties. I'll try to underscore those as we go through this one. So the first thing is this one is given to us as a function of y. So it's presented as an x value instead of presented as a y value. So if we have a function of y, we're going to integrate with respect to y instead of integrating with respect to x. So with arc length, if we're given a function of x, we're going to integrate with respect to x. If we're given a function of y, we're going to integrate with respect to y. So we're going to integrate with respect to y here on that interval. We know we need the derivative. Right? We need the derivative there. So we're going to use this formula. This is the one if you have a function of x. This is if you, I didn't write it over here. So, well, I'll write it down here. Oh, I did, right there. So if it's a function of y, you're going to integrate with respect to y, so it's x prime that we need. So let's go ahead and find x prime. Bring down the 4, it cancels with the denominator, subtract 1 from the exponent. Here we're going to think of this as y to the negative 2. So we bring down the negative 2, and it's going to do the following. If we bring down negative 2, it's going to cancel with that 8 and give us a 4. And if it's y to the negative 2, when we subtract off 1, what do we end up with for the exponent? So it's y to the negative 2. We bring down the negative 2, subtract 1, we get y to the negative 3. So there is our x prime. We then have to square it. So this is, again, in that a minus b form. I'm thinking of this is a, this is b. The minus sign is not part of a or b. So when we square it, this will be y cubed squared minus 2 times a times b plus b squared. Okay, so a minus b, quantity squared, a squared minus 2ab plus b squared. Here is how we know that it's a sneaky perfect square. If we do the middle term simplification, y cubed times y to the negative 3 is y to the 0, which is 1. 2 divided by 4,
Negative.
so we end up with a negative half. That is how we know that we're dealing with this perfect trinomial pattern. If that is not negative 1/2, then you can simplify everything and just continue on and substitute it in. The only way it's a sneaky perfect square trinomial if that is negative 1/2. Because when we add the 1 to both sides, there's only one way that you can add 1 and only change the sign of the middle term. So this trinomial thing only works when the trinomials are identical except for the sign. There's only one way that can happen. There's only one way that you can add 1 to this middle term and end up with the same magnitude. This has to be negative 1/2. It has to be negative 1/2, so when you add 1, you end up with positive 1/2. That's the only way the middle terms can be the same in magnitude. If this middle term was any other number and you add 1, you're going to end up with a number with a different magnitude. So if you don't get a negative 1/2 there, then you know that it's not this special case. So now we can integrate from y equals 1 to 2. We're going to take the square root of this thing down here. We know it's going to factor into a plus b quantity squared. So we start with a minus b, we end up with a plus b. And when we have this sneaky perfect square business, the pattern is going to be very recognizable. You're going to end up integrating a function that looks exactly the same as the derivative, except for the middle term. It'll be a minus or a plus. It'll be opposite. It'll be a minus to a plus. And then we can use the power rule. Y to the 4 over 4. Add 1 to this exponent and get negative 2. Divide by negative 2. 4 times negative 2 is negative 1/8 down there, over there. Now we're going to plug in the 2. 2 to the 4 is 16. 16 divided by 4 is 4. Minus 2 to the negative 2 is 1/4. And 4 times 8 is 32. And then we subtract off antiderivative evaluated at 1. So we subtract off this with the 1 plugged in. So it'll be a minus there and a plus here. So we'll end up with that. $32 is the common denominator. This one needs to be multiplied by 8. No, that needs to be multiplied by 32. This is over 1. So multiply by 32, and we get 128. This one gets multiplied by nothing. 4, that gets multiplied by 8. That gets multiplied by 4. So whatever that simplifies to. So 124 minus 1, 123. Divided by 32. So that'll be our arc length. Okay, so those ones are little kind of like Easter egg hunt type things. Look at those carefully, see if you can make sense of it. We can talk about it again on Tuesday if you're feeling like it is too much of a mystery. Question?
Just to clarify what you said, so this only works for perfect square if that middle term is -1/2, essentially.
100%.
And would you say, even though it rarely works this way, that it's always worth checking for?
Yeah, it's always, it's good. It should come out. The thing that is tempting is to write this as y to the 6th and and to start doing math on these things and to get it out of order. The best strategy, I will tell you on the test, if it's a perfect square trinomial technique, I'll tell you. I'll warn you just so that you're not going down a rabbit hole. It's a good strategy when you're doing, if you end up with an a minus b here, it's a good strategy to pause and not simplify these things right away. And if you do get that, then you know.
Gotcha.
And if you don't get that, then you can simplify and do regular, what you normally would do when you square something to simplify it all. It's just that in this case, simplifying it too soon can be not helpful. Next.
So where would we go from like our bottom 1 plus x prime squared if our 1/2?
We'll do an example of that now.
Okay.
Yeah, so if we don't have this perfect square trinomial thing, there's all sorts of ways that it can work out. So let's take a look at one that isn't as nasty as that. So here we're given a function of y. So again, if we're given a function of y, we look on the y-axis. If we're given a function of x, we look on the x-axis. And we are in need of the derivative here. So this will be 3/2 y to the 1/2. There's the derivative. So this derivative is not an a minus b. It's just a single term. So we know right away we're not dealing with any perfect square trinomial business. So then we square that derivative. And we'll get 9/4 times y. And then we're going to add 1. So we get 1 plus x prime squared That's just 9/4 y plus 1. So here, when we go to our arc length formula, s equals integral 0 to 4, the square root of this. So no arc, no perfect square business, no negative 1/2. It's just a regular integral. What technique would be your natural technique here? U sub is the natural technique here. Now, is this substitution linear? Is 9/4 y plus 1 linear? Yeah. And what we've seen is that if your substitution is linear, you can go reverse chain rule instead of going through the whole substitution process. So let's do that. Let's use our reverse chain rule. So we have 9/4 y plus 1 raised to the 1/2 power. So we're just going to take our 9/4 y plus 1, add 1 to the exponent, divide by the new exponent. If you divide by 3/2, you get 2/3. And what does reverse chain rule then say? We take the derivative of our linear substitution, and what is the derivative of that? 9/4. And do we multiply by the 9/4 or divide by the 9/4 for reverse chain rule?
Divide.
Divide by it. So, and if you divide by 9/4, that's the same thing as multiplying by 4/9. So, reverse chain rule always works when we have a linear U sub. So this will give us 8/9. We plug in our upper limit of 4. We're going to get 10 to the 3/2. Then we plug in our lower limit of 0. 0 plus 1 to the 3/2 is 1. And then that's totally fine as an answer, but the better way to write this would be 10 root 10 minus 1. I would accept either, but the power of 3/2, usually we like to get rid of that if we can. We'd write it as 10 root 10. So that's what a more favorable arc length problem looks like.
How much simplification do you want on exams?
At least to here.
Oh, okay.
Yeah, that would have been fine right there. But the 3/2 things, it's a good habit if to get into. I wouldn't tick off for not doing that, but
All right, so you don't have to simplify down to the answer. You can leave it
so it's a good question. This is an exact answer.
yeah.
If you type it into your calculator, you get an approximate answer. So the square root of 10 is an irrational number. As soon as you type it into your calculator, you're getting an approximation. 99% of the time we want an exact answer, so we won't put in the pi, we won't put in the square root of 10 into a calculator. We'll leave the pi, leave the square root of 2, leave the square root of 10.
Yeah.
So that's 99% of the time, that's the preference.
Yeah.
So unless the problem says find an approximation, then always leave your square roots in.
Okay.
So unless it asks for an approximation, it means leave it in exact form.
Okay. On the exam, can we just after the definite integral, just that be the answer?
This right here,
No, the step after that?
this, yeah.
Yeah. All right, that can be the answer. For
I think I get you. I mean, if there's a boatload of stuff, you should simplify it.
Okay.
You don't want to just leave it like that.
Okay. All right.
Yeah, and I'll usually try to make this piece not this is about as complicated as I would expect.
Okay.
It shouldn't be too complicated. We'll look at some sample questions. So, and that brings up a good point that I want to mention. So our review, unfortunately, I am going to be out of town on our review day. So I spent 8 hours in the last week creating, so I'm looking at the review for our first test. And so what I did and it's totally up to you guys, if you want to come in on that day too. I'm going to try to find a sub to work through some problems. But what I did was, in the last week, I created a video solution for every single one of these review exercises. So that every year, every semester, you can never get through all of those review questions anyway. And so I figured, okay, well, if I just do a video for each one of those, that'll be, I won't be here, but that'll at least give you a solution for every single one, walk through step by step. And I also created this page yesterday because it felt like there was a little bit of confusion on the geometric interpretation of an integral. So I chose a circle of radius 4 and went through all the 4 possibilities to try to help reinforce what the geometric interpretation of an integral is. So all of these are representing semicircular areas. And the area for this circle of radius 4 would be pi r squared, and for the semicircle we would divide by 2. So under that review section, you will find all of the video for all these things, plus this extra kind of review on how the geometry of a semicircle and its integral are connected. Okay, let's go back to where we were. So that one. All right, so here's another one that's not a perfect square trinomial. This one is. So I'm not going to go through another one of these perfect square trinomials, but I've put this one up here and I've put the answer there so you can try it before Tuesday and see if you can go through that process on your own. Let's go ahead and look at this one. So this is given as a function of x with an x interval, so we're going to integrate with respect to x. For all of these for all these arc length ones, we need a derivative. So we're going to start with the derivative. Any calculus problem, if you're stuck on step 1, take the derivative. And then hopefully it'll start blowing out cobwebs. So 3/2 times 2/3 is 1. So we end up with x squared plus 1 raised to the 1/2 power. Are we done?
No, you gotta take the derivative of the inside.
Chain rule. So we bring down the power, subtract 1, and then multiply by the derivative of the base. The base has a derivative of 2x. So there is our derivative. Y prime squared. So if we square this, the squaring of the square root will be x squared plus 1, and then we want to square the 2x, and we'll get 4x squared. Usually we'd write that in front. We'll do that in a second. So there's y prime squared. So this tells us that our arc length s is going to be the integral from 3 to 9 of the square root. We have our y prime square. We have to add 1 to that. So we're going to end up with, let's see if I if I distribute this out, let's see what happens. So we're going to get 4x to the 4th plus 4x squared. And then we're adding 1, that one right there, dx. Can that trinomial inside the root, is that a factorable trinomial? Is that a perfect square trinomial? Let's check. So if that were factorable, it would have to be 2x squared and 1, right? That's the only way it could possibly be factorable. So let's see. Squaring this gives 4x squared. That checks. Squaring the b gives 1. That checks. And then the middle term is going to be 2 times a times b. So a times b is 2x squared. And then if we double 2x squared, we get 4x squared. So that is the right factorization. So that is a perfect square trinomial. It's not one of those sneaky perfect squares, but it is a perfect square trinomial. So we have that. And then we should be able to square root of the square. So we're going to have the integral from 3 to 9 of 2x squared plus 1 dx. And that we can integrate very nicely. space. Plugging in the 9, we're going to get 9 times 9 times 9. So that's 81 times 9. That third 9, I'm going to wipe out a 3 in the denominator, and 3 will go into 9 3 times. Plus 9. And then we're going to subtract off the antiderivative at 3. So minus. When 3 goes in here, we have 3 3's. One of them is going to cancel, so we have 3 times 3 times 2. So that's 18. 3 goes into there, we subtract it off, so we get that. So whatever that all adds up to. If someone has a calculator, you could tell us. No, that's negative 12.
41.
41 total. Somebody double check. You agree 41? Someone confirm? That doesn't seem right.
No,
That doesn't seem right. Because this is going to be 240, this is going to be 486. So 474? That tracks more. 474. The hard part, type it into your calculator. Okay, so then here's another perfect square trinomial, the sneaky one. So try that one over the weekend. Go over it on Tuesday. Many times, if you just take a random function and someone says, find the arc length, you are not going to have a function that's integrable. 99% of the time, you will not. So let's take a look at this. So y equals x squared, very simple function. Its derivative is 2x, and the square of its derivative is 4x squared. So the arc length formula here would be the integral from negative 1 to 1 of the square root of 1 plus 4x squared. That is not integrable by you yet. We will learn a technique to integrate that, but at this stage you don't know how to integrate that. Whoops. So hopefully you're familiar with using Desmos for integrals. So all we have to do, if we're asked to do one of these things numerically, we do. Has anyone not used Desmos for integration before? A couple of you? So you can use Desmos, you can use a graphing calculator. If you have to do something numerically, Desmos is super simple. Type in int, boom, it creates the integration symbol, limits of integration. The thing here, we have to do a square root, so sqrt automatically builds the square root, and we just do exactly what we think we should do. There's our answer. Approximate answer, not an exact answer. That is approximate. As soon as we do this kind of thing, we are approximating. That is not an exact answer. That is an approximate answer. But that's how we will get our approximate answers. Plug it into some graphing utility, some sort of software. So just make sure that you can do that with whatever software your preference is. We'll end up with something similar down here when we find y prime. We're going to end up with a function that has a square that is not going to be integrable, at least not yet. So when we square this, we're going to get 4x squared minus 16x plus 16. And the arc length is the integral from 0 to 4, the square root of that plus 1. And again, that is going to be an integrand that we will not be able to integrate. The first one we will learn how to integrate. This one, even with our technique called trigonometric substitution, that integral most likely will not be integrable. So we just have to plug it in. And when you go off to do your 4-year degree, there's a whole lot of conversation about approximations. You will take, oh man, I jumped out of the integral somehow. You will take classes that are completely focused on approximations. Because as you can imagine, in the real world, when you're collecting data, the chances of that data that you collect, what you usually do is build functions from that data, differentiate them or integrate them, and the chances of those functions that you're building being easily integrable is 0. And so you'll take all sorts of classes, and how do you approximate? How do you approximate accurately enough so that you can do whatever you need to do? Make money, bottom line. That's what all these companies want to do, is make money, right? So yeah, you'll do all sorts of cool numerical approximations. Question?
What kind of calculators are we going to have access to for exams?
Just a scientific calculator.
Okay.
Yeah, we won't do anything super complicated on the exams in terms of calculations. So, but scientific calculators, no graphing calculators, and no calculators that have the integral button. Not fair if some people have an integral button and some people don't. So no integral button calculators. Those things, those pink bricks, those things. All right, so let's pivot a little bit. Let's get back into 3 dimensions. And in this class, we've seen that we can find volumes if our volumes are nice and symmetric. So generated by rotation in particular. The same thing is true for surface area. In this class, we can find surface area if our surfaces are generated with a lot of symmetry. Again, in particular, if we do a rotation, there's a lot of symmetry. In Calc 3, you're going to find surface area of random undulating surfaces, which is much more complicated. But in here, we can find surface area for nicely shaped surfaces. And like you normally do when you're finding area or volume, you are looking at cross sections and you're trying to find the geometric object that cross section is. Is it a disk? Is it a washer? Is it a shell? Here, when we're doing surface area, if we take cross sections, what we imagine a very thin cross section being is an approximation that's using the base of a cone. We can imagine all these kind of cone bases. They call it a frustum of a cone. So the idea is that we imagine all these frustums, and then as these frustums get narrower and narrower, the surface area calculation gets more and more precise, and then we do the magic sorcery of taking the limit, and that creates a definite integral. So that is what's going to happen. We are going to end up with this idea. So here's how I want you to think about it. If we have our surface here, I imagine a point element here, so just a point, and when that point rotates around, it creates a circumference. And the length of a circumference is 2 pi r. Okay? So the way I want you to think about this, let's just look at this integral for a minute. 2 pi r is a circumference right there. So this piece right here is a circumference. And the idea is that you've got your circumference, and ds is a diagonal slant. Like we already saw that if we looked at dx, dy, and ds. ds is that diagonal, they call it a slant height. And so the idea is that if you do your 2 pi r and multiply it by the slant height, that's going to give you the area of the frustum. 2 pi r ds is the area of a frustum. And so in your mind, you imagine this circumference 2 pi r, and then you integrate it with respect to s. right? You're moving along the curve, and so that little slanted piece along the curve is ds. So that is going to be our surface area integral. The integral of 2 pi r ds, the integral of the circumference with respect to s. And then we're in the same boat that we were in with arc length formulas. The ds, we know nothing about s limits. We're not measuring along an s curve. So we have to then ditch that. We got to ditch that. And how do we ditch it? The same way we just ditched it with arc length. So we need to take away the ds and convert it to either a dx or a dy, depending on what our perspective is, vertical or horizontal. And so the ds is going to equal exactly what it equaled for our arc length formula. ds is going to turn into this square root thing right here. There is ds. The same thing that it was for arc length. And most of the time, the radius is your function. Just like we did with shells and washers and discs, the radius is almost always just the function. Sometimes we have to modify it a little bit. But the basic formula, 2 pi r ds, circumference with respect to s. And then we have to convert. If we're converting to x's, we need to convert the radius to x's. And then we have to convert the ds into that arc length piece. So let's try one of these. So there's our generic formula. We are given a function of x, right? That's a function of x. And we're going to rotate it around the x-axis. So that's going to rotate around the x-axis and and create that shape right down there when that rotates around. All right, so let's look at our formula. So I'm choosing a representative, I call it a point element, because we're not using a rectangle or a sideways rectangle. We're only rotating this single point around. So that single point rotates around and it creates a circumference. The radius of that circumference is right there. It's the function, right? That radius is the function. So let's see if we can piece together each of these components. So for surface area, we're going to use a capital S. And we're going to integrate on our interval. They tell us that the x interval that we want is 9 to 20. So that x interval is down on the x-axis. So we're integrating down here, 9 to 20. That single point rotates around. So let's do the circumference. Circumference is 2 pi times the radius. The radius is the function. So there's the 2 pi r. So the 2 pi r right there. Now ds. ds, we just jump back to arc length. ds, we already know how to compute ds from last section. So ds, we have to replace that with 1 plus the derivative squared multiplied by dx. Right? So that is just arc length. All right, so we need the derivative of our function. So we have y equals 8 times x to the 1/2. So the derivative of this function is going to be 4x to the negative 1/2. Bring down the power, subtract 1. The square of that derivative is going to be 16 over x. Now you could rewrite this as 4 over the square root of x, correct? X to the negative 1/2 is 1 over x to the half, which is 1 over the square of x, square root of x. So if we square that, we get this. So now we can come back into our integral, and we're going to rewrite this with the square root of 1 plus y prime squared. So 1 plus y prime squared times dx. So there is our new integral. So the ds is all of that. So same exact ds as we did in the last section. Square root of 1 plus the derivative squared. Okay. More algebra. Unless you have a question setting that up. Constants to the front. So we have a 16 pi that's coming to the front. All right. How do we combine two square roots? How do we multiply them together? What do you do if you have two square roots and we're told to multiply them together? Can we turn it into one square root?
1/4 root, or 1/4 power.
Not a fourth power. So if the insides matched, you might be able to do something like that. But if the insides don't match, what if somebody says, hey, what is square root of 2 times square root of 3? What does that equal? Square root of 6, right? So if you have two square roots, you multiply the insides. Right? You multiply the insides to get to the next step. So when we look right here, we are going to turn these two square roots into 1 by taking this x right there, and it's going to distribute to each of those. So x multiplied by 1 is x. X multiplied by 16 over x? 16. So we have that.
The 16 pi came from you multiplying 2 pi times 8 and then you just move it outside of the integral?
Yep, so constants can always float through.
Okay.
So constants float through derivatives, they float through integrals, they float through a lot of things. They're very stealth. The integral of this, we can just integrate it immediately. We have x plus 16 to the half, add 1 to the exponent, divide by the new exponent, reverse chain rule here, what would we divide by? 1. The derivative of this is 1. So we don't have to do any reverse chain rule piece here. If there was a 4 right here, then we would have to divide by 4 also. But there isn't. The derivative of this is 1, so the derivative of 1 divided in doesn't do anything. And then this is going to go from 9 to 20. We can combine these constants here. We're going to have 32 pi divided by 3. And then we can just focus on plugging in the limits of integration just into that part. So the 2/3 is getting multiplied by the 16 pi. All right, so let's see if we can do this. Plug in 20. 20 plus 16. 36. So we're going to have 36 to the 3 halves. That we can simplify. Minus 25 to the 3 halves. That can be simplified. So we have our constant out in front. Square root of 36 is 6. 6 cubed. 6 times 6 is 36. Times 6 is 216. So we're going to have 216 minus square root of 25 is 5. 5 cubed. 25 times 5, $1.25. So 75 plus 16, 91. They're going to agree with that. 75 plus 16, so it's 85, 91. So we're going to have 32 pi over 3 times 91. Unfortunately, the 3 doesn't divide in, so somebody has to tell us what 32 times 91 is.
Um, 2,912.
So that'll be Final answer. Is 2,912 divisible by 3? How do you know?
Because the last number is even.
That's not enough. Is 12 divisible by 3?
Yes.
Right. So for a 3 or a 9, you add up the digits, and if the new number that you get by adding the digits is divisible by 3, then the original is. So we add up here, we get 14, and then we add the 1 and the 4 and get 5. 5 is not divisible by 3, so the original is not divisible by 3. That's the trick for 3s and 9s. Add up the digits. And if the new number is divisible by 3 or 9, then the original was. So we know that's not divisible by 3.
Took me 22.5 years to learn that.
Right? How? That used to be such common conversation in high school math. Divisibility tests. I feel like it's totally missing now. All right, let's try another one of these surface areas. All right, so here's another function, square root function. It's a function of x. We're rotating around the x-axis, creating this shape. So we're going to do the same thing that we just did. We find the circumference. We're imagining the 2 pi r being a point element. So imagine this point right there. It's rotating around the x-axis, creating a circle. All we're doing is finding the arc length of that circle, the perimeter of that circle, the circumference, multiplying by ds. So circumference multiplied by ds. ds is the slanted height. So circumference times ds gives you a little frustum's area. And then we add up all those frustum areas to get the total area. So let's see if we can do that. So our surface area will be 2 pi. They give us limits of integration of 0 and 5. R. What is R?
Square root of 4x plus 6.
It's the function, right? Square root of 4x plus 6. R is the distance from the x-axis, the axis of rotation, to the curve, and that is exactly the function. So square root of 4x plus 6. That is R. And then ds. All right? We've already seen many times now that ds is found by taking the square root of 1 plus y prime squared. So we have y. Y is equal to 4x plus 6 raised to the 1/2 power. So y prime is 1/2 4x plus 6 to the negative 1/2 power multiplied by 4. Chain rule. If we write this in a slightly different way before we start to take the square. So there's y prime in a simplified form. And then we square it. And if we want to square that, we're going to end up with 2 squared, which is 4, divided by the square of the square root. The square root vanishes. So that is y prime squared.
Simplifies more.
And it simplifies more. Let's do it. Let's simplify it as far as we can. So we can divide a 2 out of everything. So that will be our simplified y prime squared. So here we go. So ds, and we're now replacing ds with the square root of 1 plus the derivative squared. There we go. So there's our setup. That's our setup. Oh man, I think I like leaving this 4x plus 6 in there, I think. Do you see what happens? We have 2 square roots. So I'm actually not going to simplify that just because I see, with a little foresight, I'm now seeing that what's going to happen with that 4x plus 6. It's going to cancel. So we have the inside of this square root, and we need to distribute it to the inside of this square root. So it's going to be sent to each of those blue blobs, and when it gets sent to the second blue blob, it's going to cancel with the denominator. So simplifying in this case didn't. We could also factor the 2 out here and cause the square roots to match again, but so there's some, and you never know. Sometimes simplifying right away is the best option, sometimes it's not, kind of depends. All right, so let's see if we can distribute properly. So this 4x plus 6, that's going to be sent in here to each of those. So 4x plus 6 times 1. Okay, I can do that. And then 4x plus 6 multiplied by that fraction with a 4x plus 6 in the denominator. Those cancel. And what are we left with here? Just a 4. And let's simplify this before we start integrating. So we have the integral from 0 to 5, square root 4x plus 10. And, all right, we're back to the integral of a square of a linear. Square root of a linear. Piece of cake. We take the 4x plus 10. It's raised to the half power. We add 1 to that and get 3 halves. We divide by 3 halves, which means multiply by 2/3. But then we have the chain rule piece. The derivative of 4x plus 10 is 4. And do we divide or multiply by that 4?
Divide.
You meant multiply the denominator?
No.
Yes. Multiply the denominator by 4. In other words, divide by 4. So we'll take that derivative and divide by 4, multiply by 4, the same thing. So we get that. Simplify our coefficients. Let's see. That's going to be 4 over 4. Those cancel, so it looks like just a pi thirds in front. So all the constants are combined on the outside. So then we look at that third 3 halves power. Plugging in the 5 is going to give us 30 to the 3 halves. Minus what to the 3 halves? 10 to the 3 halves. We'll plug 0 in right here. 4 times 0 is 0, plus 10 is 10, so we have 10 to the 3 halves. So that, and normally what we like to do is kind of get rid of that and make that 30 root 30 minus 10 root 10. And if we wanted, we could factor out a 10. It's not, again, this would be totally fine on the test to stop right there. If we wanted to simplify this a little bit, we could factor out the 10 though and write this as 10 pi over 3. And if we factor out the 10, we'll be left with 3 root 30 minus root 10. That would be as far as we could go. All right, any questions on any of those steps?
You said simply simplifying to pi over 3 times 30 to the, that, and that's fine.
Totally fine.
Okay.
Yeah, that would be fine on a test. Yep, for sure. Yeah. Mm-hmm. All right, you all try this one. Let's see how far you can get. So you've got your function. It's a function of x, so we have x limits. There is the picture of the curve. That's a function I would not expect you to be able to graph on a test. That's a complicated looking function. You wouldn't have to be able to graph that. So if that was on the test, I would give you the graph. You don't even really need the graph. You just know it's in quadrant 1 and you rotate about the x-axis. You could do it without the picture. So see if you can get that integral set up. I will take some roll while you all are doing some math. Gael, Kim, Andres, Marcus, Ethan, Sean, Max, Hayden, Annie, here, Alexander, Jay, bless you, Caitlin, Kishore, not here, Nathan, here, Mason, Maxwell, here, Caleb, wasn't he here earlier? He vanished. Sebastian, Garrett, Saxon, not here. Keturah, here. Eric, not here, right? Just look over there. Jesse, Will, Tyson.
Yeah.
Oh yeah, that's right. Yeah, were you sitting up here the first day?
Huh?
Did you sit up here
Yeah,
the
I
first day?
sat there.
Okay, all right. It's amazing how first day is, and then be live. When we substitute for the radius, is it clear to everyone that we just are replacing the r with the function? So we're rotating around the x-axis. So that radius is just the function. The function is measuring the distance to the axis of rotation. And then we need to take a derivative. It's going to look pretty messy, right? So we have the square root of that whole function. So the derivative is 1/2
You're totally right.
5x minus x to the 2 to the minus 1/2 multiplied by 5 minus 2x. All right. The chain rule piece, we've got a quadratic. Its derivative is a little messy. And then we have to square that. So when we square this, in the denominator we square the 2, and there's a square root in the denominator that when we square it, the square root goes away. So that's what your derivative squared should look like. So the 2 is in the denominator, it squares to a 4. This is a square root in the denominator, and when it's squared, the half just goes away, so we get a 5x minus x squared in the denominator. And then we have that 5 minus 2x in the numerator. There's its square. So the substitution into here is looking pretty nasty. It's the square root.
Simplify that.
I don't.
Oh, never mind.
So you could factor out an x there, but that's not going to help us. There's no cancellation with the
Yeah,
numerator.
sorry.
Yeah, it looks like there should be, but there's not. So that's what we end up with. And then once again, we have this inside business, 2 square roots. The way you combine them is to multiply the insides. And we again see this nice pattern where, okay, we multiply by 1, that's simple enough. When we multiply by the second fraction, aren't these identical? So those cancel, those 2 yellows will cancel, and we'll just be left with this numerator over 4. And that numerator will need to be FOILed out, so it's 4x squared minus 20x plus 25 divided by 4. So we'll have that. And if we divide by the 4, aren't we going to get a ton of cancellation? Well, maybe not a ton, but we are going to get some cancellation, correct? We get that the 5x cancel, we get that the x squareds cancel. Yeah.
Isn't there supposed to be a 2 pi up before the?
Oh, the pi, yeah, I don't know where that pi went. Thank you. Yeah, there's a pi out there. So don't we get down to just a constant? This is 5 halves. So the square root of 25 over 4 is 5 halves. That multiplies to the front, and the 2's cancel. And all we have left is that. And what's that integral? 1 to 4? 3. Multiply 5 by 3. There's our final answer. We will stop. Time for a weekend. Shop with me. All right, questions over the weekend, you can send me an email, you can put them in OneNote, whatever. I will get back to you. I check all weekend like a fool. You can stay here as long as you want and ask questions.
Why is it 5?
So this square root right here is going to be the square root of 25 fourths. Square root of 25 fourths is 5 halves. So the 2 in the numerator, 2 in the denominator cancel each other out, leaving just 5. You're staring at something.
Explain that again.
Yeah. So all of this stuff in front cancels. So all we have is the square root of the 25 fourths, right? This is over that. And the square root of 25 fourths is 5 halves. So that 5 over 2 is coming to the front. The 2's will cancel.
Oh,
See it? 2's will wipe each other out. Have a great weekend. Enjoy some slightly warmer weather.
For now.
Much better than these
This is your first time
single-digit
around, and this is what you're
numbers
doing.
that we've been
You're
seeing.
the smartest guy I've ever fucking met or something.
Not even close.
Who?
I had him.
Fair
3
enough.
whole years.
What's that?
I just said that for chat.
was like, just like looking
Part
at
of it.
That's great. And I was going through, I was like, that's
It helps though, right?
too
When
much
you see it
homework.
the second time, it's like, oh, how come I didn't see that more clearly the first time?
That is also true.
Yeah.
It doesn't help that I wasn't here for like the last half of the semester,
Yeah,
so that's
yeah.
like more familiar.
That part could be very different. All right, have a great weekend. You too. Oh, whose bottle? Did someone? Oh, okay, good.
I think I got to like.
Have a great weekend.
I've got 3, 4.
Absolutely. Let me just hit pause on the recording.
I think the first 2 are relative.